A series of lectures by Professor George Phillies, based on his book, Elementary Lectures in Statistical Mechanics. And stand by for our future lecture series including Introduction to Mechanics, Harmonic Oscillators, Polymer Solution Dynamics, and Game Design. We have now reached the core lecture in the course. The issue at hand from the last chapter is how we calculate, for example, the pressure in a room. The pressure is a function of time, or maybe some most typical value of the pressure that corresponds to the thermodynamic pressure that does not change with time. In principle, we can calculate the pressure, the force on the walls, using Newton's laws of motion, but there are some staggering obstacles in the way. There are 10 to the 25 coupled coordinates involving all of the atoms. The atoms put forces on each other, and therefore all of those coordinates are coupled to each other. To integrate those coordinates, we'd need boundary conditions, starting values for all of the coordinates, and there is no known means of measuring all of the positions and all of the momenta of all of the atoms in the room. And if you could measure it, you'd end up with 10 to the 25 many significant figure numbers, and there's no known way of storing all of those numbers. To make life even worse, there are various sorts of problems in physics. In some, the error increases linearly and quadratically in time if you make a mistake in the starting values, but the gas problem is chaotic. The error increases more or less exponentially in time if your starting coordinates are not totally exact. That's a very large problem. The solution is provided by the simple observation that this impossibly difficult calculation doesn't seem to matter very much, because next door, completely different set of atoms and starting positions, the pressure is the same. What we do is to break the pressure into two parts. The two parts are the ideal part and the concomitant part. The ideal part is the part that is the same in every system. For example, it's the thermodynamic pressure, the thermodynamic chemical potential. It's the variable that is hiding behind all of those molecular fluctuations. The concomitant part is the part that is determined by exactly where the atoms are. The method we use lets us calculate the ideal part of any mechanical variable. In fact, it also lets us calculate statistics as to the random thermal processes that are giving us the concomitant parts, the parts that depend on exactly where the atoms are. However, we can't calculate the pressure in any particular system at any particular time. Fortunately, that's not an important difficulty. So what do? We break the universe into two parts. The system, the part we're interested, and the bath, the term comes from thermodynamics, the part we're not interested in. Separating the two, the system and the bath, is a boundary that may or may not be permeable to moving atoms, energy, radiation, or whatever. Now we advance a claim about the system, namely the system has a complete microscopic description. A classical description would say that all the atoms have coordinates and their canonically conjugate momenta. In a quantum description, we would say that multiplying all of the basis vectors are amplitudes and phases, and we can generate a list of all of those amplitudes and phases, or coordinates and momenta, and that is a complete microscopic mechanical description of the system. A state of the system is a list of all of the variables and their specific numerical values at a given time. Because the mechanical description is complete, we can use the equations of motion of the system to calculate the values of those variables at any other time. State is a quantum mechanical terminology. However, in classical mechanics, if I tell you all of the positions and all of the momenta, I have given you a complete description of the system at a single moment in time. Following Gibbs, we now introduce the ensemble. An ensemble is a complete list of all allowed states of the system and the statistical weight, the importance assigned to each of those states. Allowed has a specific meaning we'll get to later. A single allowed state of the system is also called an element of the ensemble. An important aside, there are two sorts of variables here. There are mechanical variables which you can compute from the state of the system, say the kinetic energy of a single molecule. There are also ensemble variables that cannot be computed from knowing the state of the system. The past lecture noted operational averages in which you look at a small number of samples, a limited piece of time or examples, and do averaging over that. Gibbs replaced the operational average with an ideal average in which you include every single allowed state of the system and give each state its ideal statistical weight. Gibbs introduced the canonical, or most fundamental, ensemble. In the canonical ensemble, one fixes, constrains, the number of particles n, the volume of the system, and assigns a temperature T. T is an ensemble variable. It does not choose which states are allowed, but it does enter the statistical weight. There are a vast number of other ensembles which are described in the book. Gibbs also supplies a prescription, the ensemble average. To determine the average energy, or the value of any other mechanical variable on average, you average it over all states of the ensemble using a statistical weight assigned by Gibbs, namely the statistical weight W is the exponential of minus beta E. Here beta is 1 over kT, K is Boltzmann's constant, T is the absolute temperature, and the normalizing factor Q, the partition function, has a specific physical meaning, namely Q is determined by the Helmholtz free energy A, which is an ensemble variable. Therefore, from the ensemble calculation and the sum of states to get Q, you can determine the value of all thermodynamic variables. In statistical courses in math, the weighting factors are usually taken to be normalized, meaning that Q would be 1. That is not the case in statistical mechanics. The weighting factors are not normalized because the sum of the weights has a particular physical meaning. Where did Gibbs find ensemble averaging in his two key equations? They're a new law of nature, like Maxwell's equations. They aren't derived from something simpler. They actually arise de novo. Gibbs makes a great effort in his book to show why his laws of nature are reasonable, namely, they are in agreement with the laws of thermodynamics. We are now done with Chapter 3 of my book. Everything after this is simply an illumination, an example, something to show you how to use the basic laws of nature that we have now completely described.